So let's start then by having a look at some examples. And first of all, we're going to look at the list. Now, the list is actually built as an interface. We can't instantiate the list itself. Instead, the list is an interface from which specialized versions of this list are built from, and we instantiate those, like the array list and the linked list. They draw from the properties of list. They are both types of list, you could say. They just have a slightly different behavior. So actually, let's have a look at that. That might give us something a bit more tangible to get our heads around. So let's look at the linked list then. And if you're unfamiliar, linked list is a particular data structure and contain items, objects, let's say, in a list, and the behavior is such that each node, each position, each item within the list has a pointer, a reference to the next one in the list. So, okay. Let's see a visualization of this actually, this might help us. So block that you see in the middle of the screen, path, linked list, that's an object of the linked list collection class itself. And you notice that has a reference for the first object of the list. So that little arrow there pointing towards the first object, again another box there, representing an object, that's first step, and then that object, well, it holds two, it's got, it will have next and previous, but in this particular illustration, if we were only working on a singly linked list basis, we wouldn't have previous, or prev as it's abbreviated to, we just have next. So we can only go to the next object in this list. Okay, so this is assuming it's not built in Java. Let's say we're in C++ just for this moment, and we've only got access to the next one. Okay, and then we just look at the next one. We look at the reference, go to the next one, and move to the next one, and then move to the next one. Okay, so we'd have to iterate through the list to actually get to the particular object that we're looking for. Okay, so as in Java and using the linked list collection class, we can also go backwards as well. And you'll notice that the full implementation of the linked list collection in Java has also last as the reference in the linked list object itself. So an instantiation of this linked list collection class will have a first and a last node reference. Okay, so useful for going back and forth. You can start at the end and work backwards, or you can start at the first one and then go forward. Okay, and then go back and forth as you desire. Okay, so there we go. That's the linked list there, and that's useful for certain things. Flexibility of inserting items in the middle of a list, of course, that's one of the advantages of linked lists when we talk about data structures. A bit harder with a traditional array because you've then got to move everything down or up, vice versa, if you are deleting or adding items into the array. ArrayList is a bit more flexible, of course. But with a traditional array, the linked list is useful for mid-list operations. Let's now move on and actually have a look at the array list. And it's combining the features of a list as well as traditional arrays, which you saw the statically defined ones with elements. So it draws the indexing from the statically defined arrays, which we saw previously. So we've got index positions. We don't have to start at the first element and then work our way through. It do actually have index positions. Okay, it's just a question of whether we know them at once, because the array list, it's coded in such a way that we can actually add items to the list without having to specify the index position at which we are going to insert them. Okay, objects are actually appended, they're actually just added to the end of the. Okay, so the array list, as I say, it draws the indexing from the array, but it also has dynamic aspects from the list too. So it's a kind of a combination of both of those unique data structures. So it's a convenient way to just collect items. So we could actually, if we created a series of student objects, drawing on what we did last week, we had a student class and we created a few objects representing multiple students. We could contain those students in an array list. Okay, so that might look something like this. Unlike the linked list where we have references to each node within the list can refer to the next one, the one that's added after it. That's not the case with an array list. Instead, we have a central instantiation of the array list, and you'll see there we've got the index positions, and those positions have references to a particular object. We've got three in this case. We've got three student objects, Nick, Charlie, and Sophie, and they are, if they're added in that order, then Nick would be inserted in the 0th position. Like traditional arrays, they start at 0, and then the next one to be added, calling the add method, is then appended. It's added after what's the end of the list, which will be put into position 1, and then the third student to be added, the Sophie object, would be added in position 2. Okay, so slightly different methodology there, indexing as opposed to having a chain, a sequence of nodes in the linked list. So I hope that distinction makes sense. That's going to be quite a crucial distinction to make between those two list implementation and of course the linked list. Let's now change focus a little bit. We're still looking at collections, collection classes. Look at the hash map now. The hash map different category from list. Okay, so linked list and array list come under the list category. Hash map, different category, different methodology. Okay, we add items to the array list. It does have an integer, an index position, and so do hash maps. But with a hash map, we actually go by a key and value pair. So as I say, its backend is built around an array, elements that are indexed, but the position within the array is actually calculated dependent upon the key. Now, the advantage of the hash map is we can have a string as a key. Because remember, with our arrays, we're limited to integers, aren't we? Which possibly for small size collections, it may not be necessary to know or memorize exactly where they are within the one. You would use the name as the key to look up their number. I want to call them, text them. Okay, so we actually have that as a series of characters, don't we, as a string. So with a hash map, we can actually convert string data by a process of hashing, the conversion from string or characters to numerical values, so that we actually can search the collection via a string rather than the integer index position. Okay, so this is the process of hashing is the conversion between a character and a number. And to do that, we have to refer to the ASCII values of each character. Now, we're going to come on and have a look at that, but here is a visualization of this. So hash map furthest left that's the instance of that, and I think the default size is 16 elements allocated. Again, it can expand and contract as necessary. And in this particular case, if my key, my string, is my name, I can use that. I can actually convert those letters, N-I-C-K, to a numerical value via a hashing method. HashMap takes care of that for you. You just have to provide the string literal. It will work it out for value, and then it actually does modulus to get it down the size, because we don't want to have like 3 million different elements here. So it'll actually cut it down to size. But the key being is that we can then use the reverse process to look up this position via the name. Okay, and this particular hash map node, its value, so once we type in the key, you get the value, which is the nick objects with my details and the object of the student class. Okay, so it's a different methodology to searching purely by integer index. Here we can use a string, literal, convert that to the appropriate integer index, and then look up the details that we need.